In this video, we're going to look at some practice problems relating to the density functions introduced in section 7.1. Our first example is going to be looking at the distribution of heights of basketball players in a specific league, and it's going to be given by the density function p of x. So let's look at this graph here. First of all, on the x-axis, we're going to have our height given in feet. So we have heights of 4 feet, 5 feet, 6 feet, 7 feet in between. Because there's nothing in between 4 and 5 feet and anything greater than 7 feet, we know that all basketball players in this league are going to be in between 5 and 7 feet tall. On the left-hand side, or the y-axis, we have the fraction of players per feet. So we looked at this in the previous video, that this axis is not going to be represented necessarily by the fraction of players, the percentage, but the standardized percentage where I divide by the number of feet. In this case, if you're thinking about a histogram, we would divide by the age group, but since we're not dealing with that, we just have these values here, this 8/9 and 4/9, which we're going to represent with 0.88 and 0.44 as approximations to those values. So let's answer some questions about this density function, and we can use these kind of answers to deal with a lot of different density functions. So the first question is, what percentage of players in the league are between 5 and 6.5 feet tall? We learned in the previous video that if we want to find the percentage of a population with a certain characteristic using this density function, we are looking for area under the curve. We are looking for the integral. In this case, from 5 to 6.5 of p of x dx. So looking at our graph, we're going from 5 to 6.5. We are looking for this area. And since that's a triangle, we can find that area by just saying this is going to be 1/2 the base times the height. The base of that triangle is 1.5. That's the 6.5 to 5. And the height of that triangle is 0.88, given by that value on the y-axis. If we multiply these together, this will give us about 0.66. So the question is, what percentage of players in the league are between 5 and 6.5 feet tall? In this case, it would be 66% of players. So similar question, but a little more detail. If we know that there are exactly 200 players in this league, we could ask the question about how many players are between 5 and 6.5 feet tall. From our answer in A, we know that that's going to be 66% of all players. So the answer here should be 66% of the 200 players, which is going to be 132 players are in between 5 and 6.5 feet tall. All right, another question here. What percentage of players in the league are taller than 6.5 feet tall? So if we go back to our picture, we're looking for the area. In this case, we're looking from 6.5 to 7. We're going to be finding the area of this trapezoid. Note, to find the area of the trapezoid, you could find the area of this big triangle and subtract off the area of this small triangle. You could use the formula for the area of a trapezoid, but we're going to do one better, and we are going to say that since this is the rest of our graph, 6.5 to 7, we know that it's going to be 100% minus our answer in A, part A, because that was the rest of the graph there, and it has to all equal 100%. This is going to be 100% minus 66%. This is going to be about 34%, or 1/3 is what we're really going to be getting there. And you can find that value by finding the area specifically, but they really should match up. I think if you do find the area, you'll get a 0.33. And the reason it's not exact is because we're using an approximation. on the y-axis there to start with, but it's about 2/3 and 1/3. All right, next question. Are more players taller than 6 feet or shorter than 6 feet in this league? In this question, we're not going to find the exact values of what percentage of players are greater than 6 or less than 6 feet, but we can just look at the graph here and think about which area is going to be bigger, to the left of that line or to the right of that line at 6. And I think it's pretty clear in this case that it's going to be taller than 6 feet has more, as the area here is going to be bigger than the area there. All right, and the last question related to this is that p of x is a function, and we can write it as a function. In this case, it needs to be a piecewise function here. So we are going to write p of x as a piecewise function where there's two parts. There's going to be the part related to the first line and a part related to the second line. So we're going to find each of those separately. So the first line, we have 2 points on that line. We have the point 5, 0 and the point 6.5, 0.88. To find the equation of the line, we need to find the slope. The slope is going to be y2 minus y1, 0.88 minus 0. 6.5 minus 5 is going to be 0.88 over 1.5, and I'm just going to leave it like that. We can plug this into the point slope form. That's going to be y minus y1, which is going to be 0. It's going to be equal to the slope times x minus x1, which is 5. And we will write that as our line here, 0.88 over 1.5 times x minus 5. And this is the line from all the x values from 5 to 6.5. Now let's do it again. We need to find the equation of that red line. So we're going to look at another 2 points here. We have the point 6.5, 0.88, and the line 7, 0.44. We find our slope, 0.88 minus 0.44. We have 6.5 minus 7 should give us a 0.44 over negative 0.5. And again, we can plug this into the point slope form. Our y1 maybe is going to be 0.44 equals the slope times x minus 7, using that second point there as our y1 and x1, where we used the first point last time. Plugging this in, we have 0.44 plus, or I should say minus 0.44 over 0.5, x minus 7. This is going to be from x in between 7, or 6.5 and 7. Note that we are adding 0.44 to the other side there. And there's one more piece of the puzzle that we're going to say, and that is that this function is going to be 0 otherwise. We don't really draw that part of the function, but this function is 0 everywhere else, as the percentage that the basketball players are going to be less than 5 or greater than 7 is 0. So this is the way that we could document this function. The more important part of this exercise is that if you're given a function that looks like this, can you deal with it? Not necessarily can you find the function from the graph. And that's more of an algebraic topic. So let's move on to another question now. This question says that given this density function p of x as c times x, let's calculate the value of c. So because we know this is a density function, we know some stuff about this function. Mostly that we know that the integral from negative infinity to infinity of p of x dx equals 1. We use that fact a little bit on the previous page, that the total area under the curve is 1 or 100%. In this case, negative infinity to infinity has to be 1. However, with the information that we're given, we know that this function is 0 everywhere else except for 0 to 20. So we know that this integral is going to be equal to the integral from 0 to 20 p of x dx. And this integral is the area under the curve. So in order to find this value of c, we're finding this area. Note that this point right here is going to be the x value of 20 and the y value of plugging 20 into that function, c times 20. So that means that this y value here is c times 20. So the area under the curve here is going to be the area of a triangle, 1/2 base times height. The base is 20, and the height is 20c. And that whole area has to be equal to 1. That's what we're saying. That whole area has to be equal to 1, 100%. So solving this equation, this is going to give us 20 times 20 is 400, divided by 2 is 200c equals 1. So c is going to be the tiny number 1 divided by 200. This is the lone value of c that makes this function a density function. If it were any other value, then the area under the curve would not equal 100% of the stuff that we have. Right, and one more question that's a lot different than the other two, and that is, for each of the following scenarios, let's graph a possible density function representing crop yield in kilograms from a field under the given circumstances. So this time we're not looking at heights of basketball players, we're looking at crop yields, how much crops are produced in the given circumstances. So in all of these, we're going to have the same axes. The right-hand side is going to be the yields or the right-hand side. The x-axis is going to be the yields in kilograms. And the left-hand side is going to be our percentage, our per kilogram. The same thing that we've been doing every time, the standardized percentage or fraction of what we're talking about there. So there are many different answers for these questions, except for the first one, there's only one answer, I should say. But for B and C, there's going to be lots of different answers. First one says, all yields from 0 to 100 kilograms are equally likely, and the field never yields more than 100 kilograms. So first of all, we know that it's never going to be more than 100. So if we're past 100 or lower than 0, as we can't have a negative yield, we will have a 0 function. But if all yields from 0 to 100 are equally likely, then that means that the area is going to be the same no matter what I talk about, which means this has to be a straight line. So this is going to be our density function, p of x. A straight line means it's equally likely. If you think about any 2 points here, you look at the area under the curve. Doesn't matter what area you're going to be looking at, it's going to be the same no matter where we are. All right, second one says all high yields are more likely than low, and the maximum yield is 200. So let's put this 200 here. And we know that there's going to be a higher chance of a high yield than a low yield. So there's lots of different answers, but one such answer might be something like this. So this is something that's saying that if the area under the curve, if we have higher x values, is bigger than it is for lower ones. Now, there's lots of different answers. You might have something that's a straight line. You might have something that kind of looks like this, and maybe tapers off a little bit. There's no one right answer for that question. And the last one says a drought makes low yields most common, and there's no yield greater than 30. So let's put an answer of 30 as the highest yield. And again, we're going to have something like high yields are more common, or sorry, low yields are more common. Highest yield is 30. So this would be our function here. Again, most of the area is to the left instead of the right. In the next section, we're going to be looking at the cumulative distribution function, which is going to be highly related to this density function. In fact, it's going to be the antiderivative of that function, which is related to the area that we are talking about.